So today we're going to continue with sequences, mathematical induction, and recursion with the correctness of algorithms application. What does it mean for a computer program to be correct? Each program is designed to do a specific task, calculate the mean or median of a set of numbers, compute the size of the paychecks for a company payroll, that sort of thing. We will say that a program is correct if it produces the output specified in its accompanying documentation for each set of input data of the type specified in the documentation. Assertions. Consider an algorithm that is designed to produce a certain final state from a certain initial state. Both the initial and final states can be expressed as predicates involving the input and output variables. Often, the predicate describing the initial state is called the precondition for the algorithm, and the predicate describing the final state is called the postcondition for the algorithm. Here are pre- and postconditions for some typical algorithms. Algorithm to compute a product of non-negative integers. Precondition, the input variables m and n are non-negative integers. Postcondition, the variable p equals m times n. B. Algorithm to find the quotient and remainder of the division of one positive integer by another. Precondition, the input variables a and b are positive integers. Postcondition, the output variables q and r are integers such that a equals b q plus r. And r is greater than or equal to 0 but less than b. Algorithm to sort a one-dimensional array of real numbers. Precondition would be the array of real numbers. The postcondition would be the array of real numbers, but the property is that each element is less than or equal to the second element, or the elements after it. Loop invariance. The method of loop invariance is used to prove correctness of a loop with respect to certain pre- and post conditions. It is based on the principle of mathematical induction. Suppose that an algorithm contains a while loop and that the entry to this loop is restricted by a condition G called the guard. Suppose also that assertions describing the current states of the algorithm variables have been placed immediately preceding and immediately after the loop. There's missing a word, immediately preceding and immediately within the loop. The assertion just preceding the loop is called the precondition for the loop. Oh, it's following. And the one just following is called the postcondition for the loop. The annotated loop has the following appearance. Precondition, while G, statements in the body of the loop, and the postcondition after the while. The definition. A loop is defined as correct with respect to its pre- and post-conditions if and only if, whenever the algorithm variables satisfy the precondition of the loop and the loop terminates after a finite number of steps, the algorithm variables satisfy the postcondition for the loop. A loop invariant is a predicate with domain a set of integers which satisfies the following condition. For each iteration of the loop, if the predicate is true before the iteration, then it is true after the iteration. Furthermore, if the predicate satisfies the two The following two additional conditions, the loop will be correct and with respect to its pre and post condition. The predicate is true before the first iteration of the loop. If the loop terminates after a finite number of iterations, the truth of the loop invariant ensures the truth of the post condition of the loop. Following theorem, called the loop invariant theorem, formalizes these ideas. It was first developed by this gentleman here in 1969. While a loop with guard G, let a while loop with guard G be given, together with pre and post conditions that are predicates in the algorithm variables. Also let a predicate I sub n, or I of n, called the loop invariant be given. If the following four properties are true, then the loop is correct with respect to its pre and post conditions. Basis property. The condition for the loop implies that I of O of 0 is true for the first iteration of the loop. Inductive property. For every integer k is greater than or equal to 0, if the guard G and the loop invariant I of k are both true before an iteration of the loop, then I of k plus 1 is true after an iteration of the loop. Eventual falsity of the guard. After a finite number of iterations of the loop, the guard G becomes false. Correctness of the post condition. If n is the least number of iterations after which G is false, and I of n is true, then the values of the algorithm variables will be as specified in the post condition of the loop. The loop is designed to compute the product m times x for a non-negative integer m and a real number x without using a built-in multiplication operation. Prior to the loop, variables and I and product have been introduced and given the initial values of I equals 0 and product equals 0. Precondition. M is a non-negative integer. X is a real number. I equals 0 and product equals 0. While I does not equal M, product equals product plus X, and I equals I plus 1. That is your loop. And the post condition is the product will equal M of X, or M times X. Let the loop invariant be I equals N, and product equals N times X. The guard condition of the while loop is does not equal M. Use the loop invariant theorem to prove that the while loop is correct with respect to the given pre and post conditions. Basis property. I of 0 is true for the first iteration of the loop, because I of 0 is I equals 0 and product equals 0 times x, which is true before the first iteration of the loop, because 0 times x is 0. Inductive property. Suppose k is a non-negative integer such that g and I of k is true before an iteration of the loop. Then as execution reaches the top of the loop, I does not equal m, product equals k times x, I equals k. Since I does not equal m, the guard is passed and statement 1 is executed. Before execution of statement 1, product old is k times x. Thus, execution of statement 1 has the following effect. Product new equals k plus 1 times x. Similarly, before statement 2 is executed, the old I is k. So after execution of of statement 2, the new I is equal to k plus 1. Hence, after the loop iteration, the statement I of k plus 1, namely I equals k plus 1, and product equals k plus 1 times x, is true, which is what we needed to show. Eventual falsity of the guard. The guard G is the condition I does not equal to m, and m is a non-negative integer. By 1 and 2, it is known that for every integer n greater than or equal to 0, if the loop is iterated n times, then I equals n product equals n times x. So after m iterations of the loop, I will equal m. Thus, G becomes false after m iterations of the loop. Correctness of the post condition. According to the post condition, the value of the product after execution of the loop should be m times x. But if G becomes false after n iterations, I equals m, and if I of n is true, I equals big N, and the product equals big N times x. Since both conditions, G false and I of n is true, are satisfied, m equals I, which equals n, and the product m times x is the result as well. Correctness of the division algorithm. The division algorithm is supposed to take a non-negative integer and a positive integer, d, and compute non-negative integers q and r such that a equals dq plus r, when and r is between 0 and d. Initially, the variables r and q are introduced and given the values r equals a and q equals 0. The crucial loop, annotated with pre and post conditions, is the following. While r is greater than or equal to d, r equals r minus d, and q equals q plus 1. Q and r are non-negative integers with the property a equals dq plus r, and r is between 0 and d. Correctness of the Euclidean theorem. The Euclidean algorithm is supposed to take integers a and b with a greater than b and b greater than or equal to 0 and compute their greatest common divisor. Just before the crucial loop, variables a, b, and r have been introduced as a equals big A and b equals big B and r equals b. The crucial loop with pre and post conditions is the following. While b does not equal 0, r equals a mod b, a equals b, and b equals r. So, and the post condition is a equals the greatest common divisor of a and b, big A and big B. So, yeah. Simple way of looking at loops. They're a more formalized way of looking at loops. And then let's see here. Section 5.6. Defining sequences recursively. A sequence can be defined in a variety of different ways. One formal way is to write the first few terms with the expectation that the general pattern will be obvious. We might say, for instance, consider the sequence 3, 4, 5, etc. Unfortunately, misunderstandings can occur when this approach is used. The next term of the sequence could be 9 if we mean a sequence of odd integers, or it could be 11 if we mean the sequence of odd prime numbers. So, the second way to define a sequence is to give an explicit formula for the nth term. For example, a sequence A can be specified by writing this equation here. The advantage of defining a sequence by such an explicit formula is that each term of the sequence is uniquely determined and can be computed in a fixed finite number of steps by substitution. The third way to define a sequence is to use recursion. This requires giving both an equation called a recurrence relation that defines each later term in the sequence by a reference to earlier terms, and also one or more initial values for the sequence. We saw that before, I think, in the Fibonacci sequence. Sometimes it is very difficult or impossible to find an explicit formula for a sequence, but it is possible to define the sequence using recursion. A recurrence relation for sequence A is a formula that relates each term A sub k to certain of its predecessors, A sub k minus 1, A sub k minus 2, etc., to A sub k minus I, where I is an integer, with k minus I being greater than or equal to 0. If I is a fixed integer, the initial conditions for such a recurrence relation specify the values of a sub 0 to a sub I minus 1. If I depends on k, the initial conditions specify the values of a sub 0 to a sub m, where m is an integer, with m being greater than or equal to 0. Define a sequence C recursively as follows. For every integer k greater than or equal to 2, C sub k equals C sub k minus 1 plus k times C sub k minus 2 plus 1. C sub 0 is 1 and C sub 1 is 2. So, would that be 2 would be 2 plus 2 times 1, 4, 5. So it would be 5 for C sub 2. Yeah. And you can substitute for k equals 3 and k equals 4 here as well. Let S be a sequence that satisfies the following recurrence relation. For every integer k greater than or equal to 1, S sub k equals 3s sub k minus 1 minus 1. Explain why the following statement is true. For every integer k greater than 0, S sub k plus 1 equals 3 times S sub k minus 1. No? They're just shifting everything by 1. In informal language, the recurrence relation says that any term of the sequence equals 3 times the previous term minus 1. Now for any integer k greater than or equal to 0, the term of the previous is s sub k plus 1 is s sub k. Thus for any integer k greater than 0, s sub k plus 1 equals 3 s sub k minus 1. Let A and B be relations that satisfy the recurrence relation that the kth term equals 3 times the k minus 1 term for every integer k greater than or equal to 2. All right. But suppose that the initial conditions for the sequence are different. If A sub 1 is 2 and B sub 1 is 1, you get different sequences. You get 6, 18, and 54 for A for the first 3 numbers, and you get 3, 9, and 27 for the initial condition being 1. So, yeah, it's definitely a different result depending on the initial conditions. The sequence of Catalan numbers, named after the Belgian mathematician Eugene Catalan, arises in a remarkable variety of different contexts in discrete math. It is defined as follows. For each integer n greater than or equal to 1, c sub n equals 1 over n plus 1 times 2n choose n. Show that the sequence follows the recurrence relation c sub k equals 4k minus 2 over k plus 1 times c sub k minus 1 for every integer k greater than or equal to 2. So you got the first few numbers here, 1, 2, and 5. To obtain the kth and the k minus 1 term of a sequence, just substitute k and k minus 1 in place of n in the explicit formula. So, you got k sub 1, c sub k equals 1 over k plus 1 times 2k, choose k. C sub k minus 1 is equal to 1 over k times 2k minus 2, choose k minus 1. Then start with the right side of the recurrence relation and transform it into the left side for each integer k greater than or equal to 2. So do a little substitution, and then the formula for n choose r. Rearrange the factors. And simplify. Cancel some stuff out. Rearrange the factors again. Do some simplification. And the formula for n choose r, which is equal to the definition of the sequence. Examples of recursively defined sequences. The Towers of Hanoi. One of the earliest examples of a recursively defined sequence occurs in the writings of Leonardo of Pisa, commonly known as Fibonacci, who was the greatest European mathematician of the Middle Ages and prompted the use of Hindu-Arabic numerals for calculation. In 1202, Fibonacci posed the following problem. A single pair of rabbits, a male and female, is born at the beginning of the year. Assume the following conditions. Rabbit pairs are not fertile during the first month of life, but thereafter give birth to one new female and male pair at the end of every month, and no rabbits die. How many rabbits will there be at the end of the year? Well, one way to solve this problem is to plunge right into the middle of it using recursion. Suppose you know how many rabbit pairs there were at the ends of the previous months. How many will there be at the end of the current month? The crucial observation is that the number of rabbit pairs born at the end of month K is the same as the number of pairs alive at the end of month K minus 2. Because it is exactly the rabbit pairs that were alive at the end of month K minus 2 that are fertile during month K, because they're not fertile in their first month of life. The rabbits born at the end of month K minus 1 were not. Now the number of rabbit pairs alive at the end of month K equals the ones alive at the end of month K minus 1, plus the pairs newly born at the end of the month. Thus, the number of rabbit pairs alive at the end of month K is equal to the number of rabbit pairs alive at the month of K minus 1, plus the number of rabbit pairs born at the end of month K. Which equals the number of rabbit pairs alive at the end of month K minus 1, plus the number of rabbit pairs alive at the end of month K minus 2. So, for each integer n greater than or equal to 1, let the number of rabbit pairs alive at let f sub n be the number of rabbit pairs alive at the end of month n. And let the f of sub 0 be the initial number of rabbit pairs, which equals to 1. Then by substitution into the equation, for every integer k greater than or equal to 2, f sub k equals f sub k minus 1 plus f sub k minus 2. Now f sub 0 is equal to 1. And as already noted, f sub 1 equals 1. Also because the first pair of rabbits is not fertile until the second month. Hence, the complete specification of the Fibonacci sequence is as follows. For every integer k greater than or equal to 2, f sub k equals f sub k minus 1 plus f sub k minus 2. F sub 0 equals 1 and f sub 1 equals 1. To answer Fibonacci's question, you calculate each value from 2, f sub 2, f sub 3, etc. to f sub 12, which you get a big population growth. At the end of the 12th month, there are 233 rabbit pairs, or 466 rabbits in all. Now you know where the term came from. You know what, like rabbits. When an annual interest rate of I is compounded m times per year, the interest rate paid per period is I divided by m. For instance, if 3% equals 0.03 annual interest is computed or compounded quarterly, then the interest rate per quarter is 0.03 divided by 4. For each integer k greater than or equal to 1, let p sub k be the amount on deposit at the end of the kth period, assuming no additional deposits or withdrawals. Then the interest earned during the kth period equals the amount on deposit at the end of the k minus 1 period times the interest rate for the period. So the amount on deposit at the end of the kth period, p sub k, equals the amount at the end of the k minus 1 period plus the interest earned during the kth period. So works out to be like so. Suppose $10,000 is left on deposit at 3% compounded quarterly. How much will the account be worth at the end of 1 year, assuming no additional deposits or withdrawals? B, the annual percentage yield is the percentage increase in the value of the account over a 1-year period. What is the APY for this account? Well, for each integer n greater than 1, let p of n be p sub n be the amount on deposit after n consecutive quarters, assuming no additional deposits or withdrawals, and let p sub 0 be the initial $10,000. Then by equation 564, with I equals 0.03 and m equals 4, the recurrence relation for the sequence is given here. So you can easily calculate it at the end of each quarter. The amount on deposit at the end of 1 year, p sub 4, can be found by successive substitution. So at the end of period 4, you would have $10,303.39. So the annual percentage yield would be 3.034%, because you're getting interest on interest. The yield is actually higher than the percentage rate. Recursive definitions of sum and product. Addition and multiplication are called binary operations because only 2 numbers can be added or multiplied at a time. Careful definitions of sums and products of more than 2 numbers use recursion. Given numbers a sub 1 through a sub n, where n is a positive integer, the summation from I equals 1 to n of a sub I is defined as follows. A sub I, it's a recurrence, a recursive definition here, where you have the sum of I equals 1 to n minus 1 terms plus a sub n. Likewise, the product is the product of factors from 1 to n minus 1 times a sub n. Prove that for any positive integer n, if a is a sequence and b is a sequence of real numbers, then the summation of the 2 sequences is equal to the sum of the two summations of the sequences. The proof is by mathematical induction. That's the property P of n be the equation given. We must show that P of n is true for every integer n greater than 1 or equal to 1. We do this by mathematical induction on n. First, show that P of 1 is true. Well, to establish P of 1 is true, we must show that the summation of A plus B is equal to the summation of A plus the summation of B for just one element, which is true because the definition of summation, the summation of the sum of A plus B with just one element is in each sequence is just A sub 1 plus B sub 1. Hence, P of 1 is true. So, now if you show for every integer k greater than or equal to 1, if P sub k is true, then P sub k plus 1 is also true. Suppose that k is any integer with k greater than or equal to 1, and that A is a sequence, and B is a sequence of real numbers, such that the inductive hypothesis is given. Show that it's true for k, with a range of I is equal to 1 to k plus 1. So now the left-hand side of the operation is like so, and you do some substitution with the definition of summation and by the inductive hypothesis. Substitute in the inductive hypothesis. And then by associative and commutative laws of algebra, rearrange the factors or the terms, and then you get to the summation of from 1 to k of A sub I, and the summation of B sub I, which equals the right-hand side of the equation, which was what was to be shown. And that is it for that one. I think we can squeeze in one more. Unless you guys want to call it an early day. Squeeze in one more. Squeeze in one more. That was 6, right? So 7. Come on now. Cooperate. All right. Now we get into solving recurrence relations by iteration. Suppose you have a sequence that satisfies a certain recurrence relation in initial conditions. It is often helpful to know an explicit formula for the sequence, especially if you need to compute terms with very large subscripts, or if you need to examine general properties of the sequence. Such an explicit formula is called a solution to the recurrence relation. In this section, we'll discuss methods for solving recurrence relations. The method of iteration. The most basic method for finding an explicit formula for a recursively defined sequence is iteration. Iteration works as follows. Given a sequence A, defined by a recurrence relation in initial conditions, you start from the initial conditions and calculate the successive terms of the sequence until you see a pattern developing. At that point, you guess an explicit formula. So, for example, let A be the sequence defined recursively as follows. A sub k equals A sub k minus 1 plus 2. Initial condition is A sub 0 equals 1. Use iteration to guess the explicit formula for the sequence. Well, recall that to say that the definition means that no matter what positive integer is placed in the box, you can get the values of the relation, elements of the relation or sequence. Now use the initial condition to begin the process of successive substitutions into these equations, not just of numbers, but of numerical expressions. So, you can substitute, and then substitute again, eliminate parentheses, and just keep adding 2 to it. So it looks like it's going to be A sub k equals 2k plus 1. Doesn't that look about right? It appears useful to use the shorthand 2 times k in place of 2 plus 2 plus 2, etc., k times. So we do so, starting again from A sub 0. The initial condition, substitution. It generally seems likely that the pattern is 1 plus n times 2. So it's 1 plus 2n for every integer n. A sequence like the one in which each term equals the previous term plus a fixed amount is called an arithmetic sequence. A sequence A is called an arithmetic sequence if and only if there is a constant d such that A sub k equals A sub k minus 1 plus d for each integer k greater than or equal to 1. It follows that A sub n equals A sub 0 plus d times n for each integer n greater than or equal to 0. So under the force of gravity, an object falling in a vacuum falls at about 9.8 meters per second, faster each second than it fell in the per second before. Thus, neglecting air resistance, the skydiver's speed upon leaving an airplane is approximately 9.8 meters per second after the first second, 19.6 afterwards, and so forth. If air resistance is neglected, how fast would the skydiver be falling 60 seconds after leaving the plane? No. Let S of n be the skydiver speed at meters per second, and let S of n be the skydiver speed in meters per second n seconds after exiting the plane, assuming there's no air resistance. Very important about the air resistance. Then S sub 0 is the initial speed, and since the skydiver would travel 9.8 meters per second faster each second than the second before, then it follows that the sequence would be an arithmetic sequence with fixed constant of 9.8, and thus S sub n equals S sub 0 plus 9.8 n. Hence, 60 seconds after exiting the plane, skydiver would be traveling at a speed of 588 meters per second. That's over half a kilometer per second, which is very fast for a human being to travel. And fortunately, the skydiver, taking air resistance into account, reduces the speed considerably. Let R be a fixed non-zero constant, and suppose a sequence A is defined recursively as follows. A sub 0 equals A, and A sub k equals R times A sub k minus 1. Use iteration to guess the explicit formula for this sequence. Now, it would be A, then RA, then R squared A, then R cubed A. So it looks like the guess would be A sub n would be R to the n times A, or A R to the n. A sequence is called a geometric sequence if and only if there is a constant R such that A sub k equals R times A sub k minus 1 for each integer k greater than or equal to 1. It follows that A sub n equals A sub 0 times R to the n. I was shown in example 5.67, if a bank pays interest at a rate of 4% per year compounded annually, and A sub n denotes the amount in the account at the end of the year n, then A sub k equals 1.04 times A sub k minus n, or minus 1, assuming no deposits or withdrawals during the year. Suppose the initial amount deposited is 100,000, and assume that no additional deposits or withdrawals are made. How much would the account be worth at the end of 21 years? In how many years will the account be worth 1 million? It's a geometric sequence with an initial value of 100,000 and a constant multiplier 1.04. Thus, it would be 100,000 times 1.04 times to the nth power for every integer n greater than or equal to 0. After 21 years, the account will be 227,000 and change. This is the same answer as that obtained in the previous example, but it's computed much easier, much more easily. So, how many years does it take it to get to 1 million? Then you calculate, you substitute 1 million for the balance and solve for t, given, and take natural logarithms of both sides, results in 58.7 years. Can't wait that long. Following box indicates some quantities that are approximately equal to certain powers of 10. 10 to the 7th, number of seconds in a year. 10 to the 9th, the number of bytes of memory in a personal computer. It's actually about probably 10 to the 10th now, give or take. number of neurons in a human brain, 10 to the 11th. Age of the universe in seconds, 10 to the 17th. Number of seconds to process all possible positions of a checkers game if moves are processed at a rate of 1 per billionth of a second, 10 to the 31st. 10 to the 81st, the number of atoms in the universe. And then 10 to the 111th, the number of seconds to process all possible positions of a chess game if moves are processed at a rate of 1 per billionth of a second. But using formulas to simplify solutions obtained by iteration. Recall the Tower of Hanoi sequence, where it satisfies the recurrence relation m sub k equals 2m sub k minus 1 for each integer k greater than or equal to 2, and has the initial condition of m sub 1 equals 1. Use iteration to guess an explicit formula for the sequence, and make use of a formula for the sum of a geometric sequence to simplify the answer. Now, by iteration, you have 2 to the 2, and m sub 2 is 2 to the 1 plus 1. M sub 3 is 2 squared plus 2 plus 1. So, m to the 4th is 2 cubed plus 2 squared plus 2 plus 1. Kind of seeing a pattern here. These calculations show each term up to m5 is a sum of successive powers of 2, starting with 2 to the 0th power equals 1, and going up to 2 to the k, where k is 1 less than the subscript of the term. The pattern would seem to continue to higher terms because each term is obtained from the preceding one by multiplying 2 and adding 1. Multiplying by 2 raises the exponent of each component of the sum by 1, and adding 1 adds back the 1 that was lost when the previous one was multiplied by 2. So, thus it seems that in general, the formula for the sum is 2 to the n minus 1 plus 2 to the n minus 2, etc., to the 2 to the 2nd plus 2 to the 1st plus 2 to the 0th. But the sum of geometric sequence theorem shows that a geometric sequence is 2 to the n minus 1 over 2 minus 1, or 2 to the n minus 1. So the explicit formula seems to be m to the n equals 2 to the n minus 1 for every integer n greater than or equal to 1. Now, checking the correctness of a formula by mathematical induction. As you can see from the 2 previous examples, the process of solving a co-recurrence relation by iteration can involve complicated calculations. It is all too easy to make a mistake and come up with the wrong formula. That is why it is important to confirm your calculations by checking the correctness of your formula. The most common way to do this is to use mathematical induction. We have attained a formula for the Tower of Hanoi sequence. Use mathematical induction to show that this formula is correct. What does it mean to show the correctness of a formula for a recursively defined sequence? Given a sequence of numbers that satisfies a certain recurrence relation and initial condition, The job is to show that each term of the sequence satisfies the proposed explicit formula. In this case, you need to prove the following statement. If M is a sequence defined by M sub k equals 2M sub k minus 1 plus 1 for each integer k greater than or equal to 2, and M sub 1 equals 1, then M sub n equals 2 to the n minus 1 for every integer n greater than or equal to 1. Proof of correctness? Let M sub 1, 2, 3, etc. be the sequence defined by specifying that M sub 1 equals 1 and M sub k equals 2 times M sub k minus 1 plus 1 for each integer k greater than or equal to 2. And let the property P of n be the equation here, the 2 to the n minus 1. Use mathematical induction to prove for every integer n greater than or equal to 1, P of n is true. So, establish P of 1. 2 to the 1 minus 1 equals 1. Now, by the definition, that works out. And the right-hand side, it works out. Thus, the two sides are equal and to the same quantity, and hence P of 1 is true. Now show that for every integer k greater than or equal to 1, if P of k is true, then P of k plus 1 is also true. Suppose that k is any integer with k greater than or equal to 1, such that m sub k is equal to 2 to the k minus 1, which is your inductive hypothesis. You must show that m sub k plus 1 equals 2 to the k plus 1 minus 1. But the left-hand side of P of k plus 1 is this, which is by the definition of the sequence and substitution from the inductive hypothesis, distributive law, and basic algebra, you get 2 to the k plus 1 minus 1, which equals the right-hand side of the equation. So it follows by mathematical induction that the given formula holds for every integer n greater than or equal to 1. Discovering that an explicit formula is incorrect. So let the C sequence be defined as follows. C sub k equals 2c sub k minus 1 plus k for every integer k greater than or equal to 1, and c sub 0 equals 1. Suppose your calculation suggests that the sequence satisfies the following formula. C sub n equals 2 to the n plus n. Is this formula correct? Start to prove the statement by mathematical induction and see what develops. Proposed formula satisfies the basis step of the inductive proof. C sub 0 equals 1 by the definition, and on the other hand, 2 to the 0 plus 0 is 1 plus 0, which is 1. In the inductive step, you suppose that k is any integer with k greater than or equal to 0, such that c sub k equals 2 to the k plus k. That's the inductive hypothesis. And then show this here. To do this, you start with c sub k plus 1, substitute from the recurrence relation, use the inductive hypothesis, and do some algebra around and substituting from the inductive hypothesis, and finish the verification. Therefore, you need to show that this here is true. Well, now this is equivalent to 2k equals 0, which is equivalent to k equals 0. But this is false since a k may be any non-negative integer. For instance, k equals 1, then k plus 1 equals 2. And so it doesn't work out. Things didn't go through in the wash. So the formula does not give the correct value for C sub 2. Hence, the sequence does not satisfy the proposed formula. And that will wrap things up for today. I believe we're going to finish up Chapter 5 on Tuesday, and which will allow us to take a quiz on Chapter 5 on Thursday. And homework for Chapter 5 will be due before class on Thursday. If it's not set to that due date right now, it will be by the end of the weekend. But in the meantime, have a good day, have a good weekend. See you on Tuesday.